In this lecture, we're going to try and study some examples of addition polymers. The number one example of an addition polymer is polyethene. So it is polyethene, and if you have some general knowledge of polyethene, they mostly make your plastic bags that you see all around. They're mostly made from polyethene. So they're called polythene bags as well. So polyethene is made from ethene, which is this, the simplest alkene. And when you talk about polythene, it would have lots of ethene molecules that would, these monomers, they would end up joining together. So I'm going to draw a few ethene molecules or monomers which will end up joining together under high pressures and high temperatures, and they would form a polymer. So high pressures and high temperatures, this double bond is going to be converted into a single bond. It would break up. So these double bonds, I removed these double bonds, and instead I'm going to draw single bonds in their place. And when you draw a single bond, when that double bond gets converted into a single bond, all these carbon atoms have now one bond less, so they end up joining with each other, and these are continuation bonds, meaning that this chain is going to continue. So you have these polythene bags or plastic bags which are used for carrying items and usually used as shopping bags as well. And the simplest or the compressed form of this polymer would be that it is this particular monomer that is its residue that's continuing and that's repeating over and over again. So I'm going to draw the simplest repeat unit, which in this case is this ethene residue, and this thing is being repeated over and over again. So I'm going to draw square brackets around this and write n, which would mean that it is being repeated n number of times. Our second example is of PVC. So the second example that we are going to study is of PVC. It's also called polyvinyl chloride. So now this PVC or polyvinyl chloride, it's generally, if you must have heard of about PVC pipes. Mostly it's used in construction. So PVC pipes are embedded in the walls. They're used for drainage pipes. So they're very commonly used in PVC. Then you've also heard about PVC tiles or vinyl tiles. Now these are very hard tiles which are used for flooring, and they have different finishes. So the PVC pipes and PVC tiles are very frequently used in construction. And what's a PVC polymer? It's made from this particular monomer. It looks exactly like ethene, except one of the hydrogens has been substituted by a chlorine. So this is the monomer that makes a PVC. And if you want to know the structure of a PVC polymer, that would look something like this. I'm going to redraw this. I'm going to draw three structures or three repeat units. So that's one monomer. Then you have another repeat unit, and the hydrogens. This is going to have one hydrogen. This is also going to have one hydrogen. So I've drawn three repeat units, and the double bonds under high pressures and higher temperatures, they're going to break up and they're going to get converted into single bonds. So all these double bonds they break up, and instead you have single bonds in their place. So once you have these single bonds in place, these carbon atoms would now link up because they need to make a fourth bond. So they make a fourth bond with each other. These two carbon atoms are making 3 bonds each, so they make a fourth bond with each other. And these are continuation bonds, meaning that this chain is continuing to bond with other monomers. And the simplest repeat unit of this PVC looks something like this. There's a Cl atom on this side, there's a hydrogen atom below this, there's another hydrogen atom and another hydrogen atom, and then you're going to draw continuation bonds and square brackets. This is the simplest repeat unit for a PVC, and N represents the number of times this repeat unit is going to repeat in that polymer chain. So that's a PVC polymer, and it's used in making tiles. And just a few more things. The name of the monomer in this case, it's chloroethene. This monomer over here, the basic building block of a PVC, is chloroethene. Our third example of an additional polymer is called PTFE, or if that's an abbreviation. If I write the full name, it's called polytetra fluoroethene. So that's PTFE, and its number one use is as non-stick plastic. So the number one use is non-stick plastic, and this non-stick plastic can be found in your frying pans and in different cooking utensils. So the properties of a PTFE that makes it suitable for this use is that it has a very high boiling point. It's resistant to heat. Plus, it's not going to stick with the food substances that you're trying to cook. So what is PTFE? PTFE is made from tetrafluoroethene, which is this molecule over here. It's basically like an ethene, except that all the hydrogen atoms have been tetrafluoro, means that there are 4 fluorine atoms attached to this monomer. So this is the basic building block of a PTFE molecule. Is called tetrafluoroethene, and that's your monomer. And if I try to make the structure of a PTFE molecule, it's going to be this tetrafluoroethene monomers. They would end up joining with each other under higher pressures and higher temperatures. So I'm going to draw these. I'm going to draw 3 repeat units of this monomer. So that's your second one. It's going to have 4 fluorines. So that's your third PTFE molecule, and under high pressures and high temperatures, this double bond is going to break. So I'm going to rub off one of the bonds. This double bond is going to break up, and it's going to be converted into a single bond. And what's going to happen is that each of the carbon atoms is now making this 1 bond less, so they end up joining with each other to complete the 4th bond, and these are continuation bonds, meaning that the structure is continuing, and that's how a PTFE chain would look like. And to draw a simple a compressed version of this exact same molecule, that would be I would draw 1 repeat unit, which is I'm going to draw the monomer residue. So that repeat unit is this, which is going to repeat over and over again. These are continuation bonds, and I'm going to draw square brackets around it. So those are my square brackets, and I'm going to write n, where n is the number of times that this residue, this monomer, is going to repeat in that particular chain. So that's your PTFE molecule. It's another example of an addition polymer. Plastics are very useful substances. They're used frequently. They're almost everywhere. Your shopping bags, your plastic toys, your electronics, they all have some plastic in it, and even your floors have plastic tiles. So plastics are very useful in everyday life. Almost everything contains some amount or some form of plastics in them. So they are polymers. They're mostly made from addition polymerization, but they have a huge pollution problem associated with them. The number one problem associated with plastics is that they are non-biodegradable. What that means is that they don't decompose naturally. So they don't decompose naturally. If you throw away plastic, then that plastic would probably be in its original form for thousands of years, and it would be very hard for you to get rid of plastics. And this would lead to a second problem, which is that they are going to occupy landfill sites. You would need to store all the or throw away all that plastics in specifically designated areas that are called landfill sites. So they occupy landfill sites. So your agricultural land is going to be affected. There would be less agricultural land available for growing crops, because there would be a lot of land that would only be used for keeping or for dumping plastics that have been used. So to avoid that problem, a lot of recycling is done to reduce the amount of plastics being produced. Plastic being produced. And a third problem associated with plastics is that if you try to burn them, harmful pollutants are produced when you try to burn them. So harmful pollutant gases are produced when plastics are burnt. And some of these pollutants are extremely harmful for the human health. For example, carbon monoxide. It's a poisonous gas. Then you have dioxins and furans that are produced, which are also very harmful for the human health. Especially they are a cause for hormonal imbalances in the human body. So they're especially harmful for children, and must always keep children away from pollutant gases that are produced when plastics are being burnt. Another fourth cause of concern related to plastics is that if animals generally they do consume a lot of things which are not healthy for them, and if there's a lot of plastics around, then some of that plastic is going to end up in animal feed, or some animals might just consume those plastics and choke on them and die from those plastics. So animals can choke and consume plastics. So a lot of animal death is also associated with plastics. So there are a number of reasons why plastic use must be avoided, and to counter that, some of the choices that are made by organizations, different people, is that there's a lot of recycling is done to avoid this problem. Similarly, use biodegradable substances. Now, if you use biodegradable substances, then your need for plastics would also be lesser. Some of the biodegradable substances that are being used is, instead of plastic bottles, a lot of companies have started using glass bottles. Similarly, instead of polythene bags, a lot of companies have started using paper bags for holding things. And there are a lot of personal choices made by different people as well that has led to a decrease in the use of plastics. And there's now an overall and there's now a campaign for an overall decrease in the amount of plastics that are being produced around the globe right now.